let me begin. So this is going to be a course on cosmology. And as I had said in my mail, this will not start from the beginning. It will in fact begin from where we ended in the GR course. But let me just briefly recall some of the things that we will need from a GR course. So, a very brief review of what we have learned there. So, we assume homogeneous and isotropic universe. This, together with choice of coordinate system, allowed us to fix a metric in this form. Where this was d theta squared plus sine squared theta d phi squared, and k could be 0 or plus minus 1. Okay, this was the most general form of the metric that we could write down based on homogeneity and isotropy. And then we also said that our universe has k equal to 0 for all practical purposes. So we will be working with k equal to 0. Okay, unless in special cases when we need, we will set k equal to 0 in all our calculations. We also fix the form of the energy momentum tensor in this coordinate system based on again homogeneity and isotropy. So you have T00 as rho, which could be a function of t, of course. Tij was p of t times gij, and Ti0 was 0. And the physical interpretation of these quantities was this was energy density. And this was pressure. Then we substituted this metric and this energy momentum tensor into the Einstein's equation, and that gave us two independent equations. One was a Friedmann equation, A dot over A square plus K over A square, which we will set to 0, equal to 8 pi g over 3 times rho. And the other one was the conservation equation, d dt of rho a cube equal to minus 3p a square a dot. So dot means time derivative. This we said is a consequence of p mu t mu equal to 0. Okay, we got it from Einstein's equation, but you could have also gotten it simply by looking at the energy momentum consumption also. And here we encountered a problem that we have three independent functions of time to begin with. A of t, which enters here, rho of t and p of t, okay, three independent functions of time, but only two equations. These are the two independent equations that we could get. And the question was how we can use two equations to solve for three unknown functions. And that problem we resolved by saying that if the energy momentum tensor comes from a single component, then there is a relationship between the pressure and the energy density, and that's the equation of state. So for single component, P is given by some function of rho. So this was the third equation. Okay, this function of rho is known from equation of state, from thermodynamics. So example was matter, non-relativistic matter, which has P equal to 0, radiation, which has P equal to rho by 3, and then the third example was cosmological constant, P equal to minus rho. Are there questions? This is, everybody remembers this? Right, so you can proceed. Now, in our universe, of course, we have all three components. We have matter, radiation, and cosmological constant. When you have all three components, then let's count the number of equations and number of unknowns again. So we have A of t, of course, is an unknown, and we have three pressures and three energy densities, right? Because there is pressure of matter, pressure of radiation, pressure of cosmological constant, energy density of matter, energy density of radiation, energy density of cosmological constant. So you have 6 plus 1, 7 unknowns. Okay, 3 pressures, 3 energy densities, and the scale factor A of t. Number of equations is 1 here, 1 here, 1 here, 2, plus 3 equations of state, 3 relations that relates the pressure to energy densities. So 5 equations and 7 unknowns.
So we are not assuming that matter, radiation, and cosmological constant are completely decoupled means.
Okay, not yet. I mean, this is the general situation. Okay. So you have, in a general situation, you have 7 unknowns and 5 equations, right? So how do you proceed? You remember how we proceeded? What did you do to solve this problem? You have 7 unknowns and 5 equations.
All of them decoupled, we consider separately for
so you assume that there is separate conservation laws in each sector, right? Matter, radiation, and cosmological constant. So you assume separate conservation laws. Which basically said that d dt of rho m a cube is equal to minus 3 pm a square a dot. Okay, this of course is 0 because pm is 0. Then we assume that d dt of rho r A cube is minus 3 PR A square A dot, and d dt of rho lambda A cube is minus 3 P lambda A square A dot. So if we make this assumption, and this assumption physically amounts to saying that there is no exchange of energy between matter and radiation, matter and cosmological constant, or cosmological constant and radiation, other than of course what is induced by gravity. Okay, the gravity induced exchange is taken care of by the fact that this conservation law involves covariant derivative and not ordinary derivative. Okay? So the fact that there is d mu, t mu nu equal to 0 means that t mu nu is not divergenceless. Okay? There is a non-trivial contribution that is proportional to the Christobel symbol, okay? And that tells you how much energy is exchanged due to gravitational interaction. So that is already taken into account. But other than gravity, okay, we assume that there is no exchange of energy between different components. Okay? So in more covariant notation, these three equations stand for d mu, dm mu nu equal to 0, d mu, dr mu nu equal to 0, and d mu, t lambda mu nu equal to 0. Now with this, let's count again. Okay, how many equations and how many unknowns. So you have three equations over here, three separate conservation laws. Okay. We have the Friedmann equation, so that's 4, and three equations of state, that's 7. So 7 unknowns and 7 equations. So you can now proceed to solve them. Okay. But now we ask, how justified is this assumption? Separate conservation law for matter, radiation, and cosmological constant. For the cosmological constant, there is a problem. This equation always holds. Why? What is the form of P lambda mu nu for the cosmological constant? It's proportional to G mu nu. It's minus lambda G mu nu, right? So that T00 is basically lambda times G0 minus lambda G00, right? So d mu G mu nu of course is always 0. So this assumption is okay. This is justified. Okay, there's no problem with this one. Okay. That just reflects the fact that rho lambda and P lambda are just constants. Okay, that's why it's a cosmological constant. So this equation is there, so you can rely on this. But between these two, matter and radiation, there can be exchange of energy. Today, it's a good approximation to say that there is no exchange of energy. Okay? And the main reason for this is because the matter is neutral. Okay? Most of the matter in the universe is neutral. So the photons are basically not absorbed. Okay? The amount of collision that a microwave background photon has with matter is negligible.
But isn't the universe reionized right now?
Okay, it's reionized, but the density is so low, right, that the collision is still very low. Right? So the one in the early days when it was ionized, there used to be a strong interaction. Right? Then once the matter became neutral, okay, the collision stopped. Okay? Later on, of course, it became ionized because of the various star formation and other effects. But by that time, the density has already dilated so much that you can ignore the interaction between photon and matter. Okay, so effectively, there is no it's a good approximation to say that there is no interaction between matter and radiation. Okay, on the average.
So So the last equation, you are considering this thing to be some lambda to be some constant, but
Yes.
suppose still the slow roll is going on, and suppose lambda is the vacuum excitation.
Yeah, then there can be exchange.
Then there can
Then
be
of course this equation of state also is not completely correct.
Okay.
Then you have to change this equation of state also, right? So instead of cosmological constant, suppose you assume that this is the energy density of a scalar field,
Right.
right? Like what you have in the case of inflation. Then of course you have to take into account the possible exchange with that as well.
And that also represents completely homogeneous and isotropic universe, right?
Yeah,
Even
because
if
as
it's slow rolling,
even if it's
still
scalar field, right? As long as the scalar field is uniform,
rolling. Yeah.
it's homogeneous and isotropic. Yes, that is the question.
In the counting that you mentioned, so there, you are saying that there are 7 equations.
Yes,
3 are these separate conservation laws.
separate conservation laws.
3 are the
Equations of state.
Equations of state,
Yes,
and there is one Friedman equation.
Friedman equation.
But
That row, yes.
what that corresponds to is the sum of the all.
Yeah. So this row is basically the sum. So this row is rho lambda plus rho r plus rho m. So let's leave this apart. Let's suppose that this equation is okay, but not separate conservation law between these two. Okay? If matter and radiation can exchange energy, then this is not true anymore. So now let's count again. We have two equations from here, one here and then the sum of these two. Okay? That's the total energy conservation other than the cosmological constant. So that's two equations. This is 3 equation over here, 3 equation of state. So that's 5 plus 1, 6. But we have 7 unknowns.
In that case, also the matter radiation, this pressure to density relation is true. Means if the interaction is there.
Well, you assume that it's like you assume that the interaction is there, but the energy interaction is small enough, right? So that you can still use the same equation of state. Right? That's what you do in statistical mechanics typically, right? I mean, when you talk about ideal gas, for example, right? A truly ideal gas which has no interaction between particles, right, doesn't have a statistical description because there's no thermalization, right? You start from any initial state, each particle preserves its energy under collision. Right? So you need some collision, some interactions to come to thermal equilibrium. Right? So you're assuming that there is some kind of interaction between matter and radiation.
Here we assume that interaction rate is less than h or something.
Well, we'll come to interaction rate. Right now, let's suppose that there is some interaction, right? If there is some interaction, then we see the number of equations have become 1 less than the number of unknowns. Okay? So you have to do something to make sure that we have some additional equation. Okay, we cannot solve the equations without any further assumption. Right? If we assume that there is an exchange of energy between matter and radiation, okay, then we lose one equation and hence we must gain back one equation somehow. Is that point clear? So this can be achieved if we make an opposite assumption, okay, that the interaction between matter and radiation is sufficiently fast, okay, so that there is thermal equilibrium. Okay. Suppose matter and radiation exchanges energy. Okay. As long as the exchange of energy takes place at a sufficiently rapid rate, we can expect that they will come to thermal equilibrium. Okay. That means what? That means the temperature of matter should be the same as temperature of radiation. Okay. So thermal equilibrium will mean that PR is equal to Tn. But each of these, PR and Tm, by statistical mechanics or thermodynamics, are themselves functions of rho and P. Okay? Temperature is, once rho and P are fixed, temperature is not an independent variable, right? there are various thermodynamic relations which tells you what the temperature is as a function of rho and P. So a relation of this kind is a relation that's relating rho r PR to rho m PM. Some combination of rho r PR to some combination of rho m PM. So that's one additional equation involving same variables. So that can supply the missing equation that we have, and we can again solve the system. Yes.
So but if we don't make this assumption,
Yes.
even then we will have 6 equations, but we will the number of variables will also be lesser because there is some relation between the matter density and this density, energy density of
Radiation. How do you know that radiation?
from what type of interaction is happening.
Well, but that requires detailed knowledge, right? I mean, how do you actually? There is you cannot write down a simple relation between the radiation energy density and matter energy density, right? So, I mean, the fact that they can exchange energy doesn't mean that there is a definite relation between their energies. Right? It depends on the whole history. So imagine that there are two systems, right, which can in principle exchange energy. Right? That by itself doesn't tell you what kind of energies the individual systems have, right?
We need some initial conditions.
You have some initial condition and evolve the system from there to figure out what kind of ratios they have. Right? That's a much more complicated process. So these are the two simple cases, two extreme limits, right? That when there is no exchange of energy, then you can assume independent conservation laws for each sector. When there is sufficiently rapid exchange of energy, then you can assume thermal equilibrium. In both cases, you can reduce the number of variables so that the number of variables and number of equations become the same. Well, I should say you can increase the number of equations so that the number of variables and number of equations agree. And you can solve the system. And we'll see later for multi-component systems in which there will be more variables, but if we assume thermal equilibrium, we'll see that there is always the same number of variables as this number of equations. Okay, just like in this case. But now we have the task of deciding in a given situation which equation to apply. Should we apply the equation that is valid assuming there is thermal equilibrium, or should we apply the equation that is valid assuming that there is no exchange of energy? Or is the situation more complicated? Somewhere in between. How do we decide that? Okay. What calculation we should do to decide which equations we should apply, and then we can go ahead and apply the equation. Is this question clear? So, the essential condition for thermal equilibrium is that the reaction rate must be much larger than the expansion rate. Intuitively, it should be more or less obvious, right? That if the expansion rate is very slow, right, then however small the interaction, if you wait for sufficiently long, it will thermal equilibrium. That's what you are familiar with, right? That system eventually thermally equilibrates, okay, given long enough time. The problem in the universe is that you don't have always long enough time, right? Because the universe is expanding. So you have to ensure, in order to have thermal equilibrium, that the reaction rate is much larger than the expansion rate. Okay. In more quantitative terms, okay, what this means is the following. Okay. So expansion rate is A dot over A. Right? This is the measure of the expansion rate. So let's call this H of T. So H inverse is the time scale of expansion. H has a dimension of 1 over time. Right? H inverse has a dimension of time, so that's the typical time scale of expansion. Right? In a time of order H inverse, the universe grows by a certain fraction. So we make this more quantitative by saying that the number of collisions of a particle in time H inverse should be much larger than 1. So take a given particle, the number of collisions that it suffers in a time of order H inverse should be large, so that it has enough time to exchange energy with other particles and thermal equilibrium. Right? That's the criteria that we'll be using for thermal equilibrium. The independent conservation is the opposite limit. So I should have said typically, okay, let me write this and then I'll explain this. So independent conservation means the number of collisions of a particle in time H inverse is much less than 1. Okay, so there is no scope of the particle exchanging energy within 1 Hubble time. Okay, in that case, you can assume that independently energies in each sector are conserved. These criteria that we have given are functions of time. As time evolves, we may transit from one to the other. And typically it happens because of various reasons. First of all, the expansion rate typically decreases as a function of time. Okay, if you recall the matter energy density, matter radiation dominated universe, right? In cosmological constant, of course, H remains fixed. Okay? But in other systems, matter or radiation dominated era, the expansion rate falls. Okay? Is that familiar? Expansion rate falls?
Yes.
It typically falls as 1 over T. Okay? A dot over A. But this one falls faster, typically. The number of collisions that a particle suffers falls faster. Okay? First of all, the reaction rate changes. But more importantly, the density of particle falls. Density of other particles.
Can you please once again explain why the expansion rate is slowing down? Because earlier what we have seen that A dot by A has with this H, suppose at today, that was like H naught times T and then some T square, and the coefficient of the T square I think was positive. So
that's the acceleration you are talking about.
okay.
Okay. That's a different calculation, yeah. So let me explain. So typically, in matter or radiation dominated era, right, A goes as 80 to the alpha with some exponent. Right? So A dot over A is basically alpha over T.
Okay.
Right?
Yeah.
So as T increases, this
Only for cosmological constant it is exponential, so it is constant.
yeah, it's constant, exactly. The acceleration that we talked about is A double dot, not ddt of this. Ddt of this is slightly different from ddt of A dot itself, right? Okay, so what happens with time is that the density of particles is falling, right? The density of particles falls as 1 over a cube. And as a result, when a particle moves in this medium, right, because the density is falling, the number of collisions it suffers, even if the reaction rate remains the same, right, the number of collisions that will suffer will be less, right, because there are less number of particles to collide with. And because of this, typically what happens is that as time progresses, you make transition from this region to this region. So systems fall out of equilibrium. Okay, they don't exchange energy very efficiently anymore, and then we can apply independent conservation law for that system. So we should keep in mind that the equations that we'll be using in cosmology are not the same equations in all era. In every era, you have to decide which equations to use: independent conservation law or thermal equilibrium. Right? Also, it's not true that all systems are in thermal equilibrium at the same time, right? That some of the systems may be thermal equilibrium with each other, some other systems may be having independent conservation laws. Right? That depends on the kind of reaction that the system has. But in either of these cases, this case or this case, you can get enough number of equations. Either by equating the temperatures of the systems, okay, that's in the case of thermal equilibrium, or by applying independent conservation laws on the system. So we'll be able to solve the equations easily in either of these cases. During the transition, of course, things are more complicated, right? Because at that time they are neither in thermal equilibrium, nor you can assume that they are independent. But typically what happens is that this time interval is short enough in cosmology that you can assume that you make a sudden transition from this to this. Basically, you say that instead of taking much larger than 1, whenever this number of collisions in a time H inverse is greater than 1, you assume thermal equilibrium. When it's less than 1, you assume independent evolution. And at the boundary, you match boundary conditions. Okay, so you just directly make transition from one kind of equation to another kind of equation. Of course, this is not strictly correct. Okay? If you want to be more careful, you have to do more work, okay, by going through the transition carefully. Okay, but for most purpose, it's good enough to say that for when this is larger than 1, you will use thermal equilibrium. When it's less than 1, you will use conservation laws, independent conservation laws.
Sir, why do the density falls at matter and luminosity?
Because it's d dt, that is conservation, that's the number conservation. D dt of n a cube is 0, typically, right? Because the total number of particles in a given moving volume remains fixed, right? So n goes as 1 over a cube, right? So as a increases, n falls.
Sir,
Yes.
so the transition from the thermal equilibrium condition
Yes.
and the independent conservation, they should be smooth because of the fact that
Yeah, this would be smooth. So in between, okay, you have a much more complicated set of equations, right? But what I'm saying is it's a good approximation, okay, at least as a first approximation, to say that this is an abrupt transition, that from H inverse larger than 1 to H inverse less than 1, the equations suddenly make a transition from this kind to this kind.
okay.
The variables are still evolving smoothly, right? So you match the variables at the end of the first evolution to the beginning of the second evolution, right? Only the equations change. Right? So you match all the variables smoothly across this boundary. Okay? But it's an approximation, of course. It's not an exact statement, right? Because you don't have a sudden transition from this to this. Other questions?
Can you repeat that? Why this rather than this greater than or less than, you can take only greater?
Well, this is just an approximation, as I said, right? That truly what you should do is that you should apply the thermal equilibrium in this regime and the independent conservation in this regime, right? And in between, right, you have to do a more detailed analysis of by taking into account how the energy exchange is taking place. Okay? It's just that if you don't want to do that work, right, you can make this approximation that you make a sudden change from here to here. That's it, just for ease of doing calculations.
So sir, is it possible for us to distinguish between rho m and rho r in thermal equilibrium?
Yes, it is possible. Even in thermal equilibrium, you can calculate rho m and rho r. How much energy density is there in matter, how much energy density is there in radiation. Right? And we will see how to do this calculation. Right? Because these are variables, of course. These are, variables that enter the dynamics, right? So you certainly have independent meaning of what is rho m and what is rho r. Right? It's just that they are not conserved by themselves. Right? As time evolves, right, you can have energy transfer between one and the other. Right? And this transfer takes place according to the law that the temperature should be the same. Right? That's the condition for thermal equilibrium. And even if some system has more energy density than the other, right, doesn't necessarily mean that the energy density is going to flow from the more energetic situation to the other less energetic situation. Right? What determines the energy flow is temperature. Right? So the temperature should be equal. Are there other questions? Okay. So having this thermal equilibrium, okay, is also useful for another reason. Okay, so let me explain that. So one of the goals of cosmology, and the main goal, is to make predictions about the present universe, right? Make predictions about the present universe from the past. So you want to know how the universe, how we have the universe that we see today, by starting from some fundamental principle in the past.
But what we do usually, we put the initial conditions today, right? In doing, try to
Yeah,
get this.
but that's what we did in the GR course.
Right.
But doesn't mean that's what we have to do, right? We want to know how it is today, the universe today, right? Starting from some basic principles, right? Okay, so we want to start from somewhere and reach today, right? But let's recall the history of the universe. Okay? So time goes this way. This is time. Temperature goes this way. Okay? Earlier time had higher temperature. So we have, in terms of temperature, the earliest we discussed was like 10 to the 15 to 10 to the 16 GeV. This is where we had inflation. Okay, this is still speculative. We don't know for sure if this is really what happened, but let's suppose that this is something what happened. Then you have T of order 100 GeV. This is standard model. Okay, and then many things happened after this, all of which you'll be studying in this course. Okay. This is T less than about a EV. Okay. This is where we ended in our course, in our GR course. This is where you have the recombination. Okay, where the electrons and protons combine to form hydrogen atom. And then, of course, many things happened even after this. The whole formation of galaxies and stars, everything happened after this. Right? The point is that from here onwards, we know the microscopic physics reasonably well. Right? We know what the dynamics is. Right? The standard model and its offshoots. This part is totally unknown. So given that this part is unknown, right, we can ask that how can you predict anything? Right? Because the initial conditions are here. Right? And we don't know what's going on here. The reason that we can predict something without knowing what was happening here is because of thermal equilibrium. Because of the fact that somewhere here, let's suppose that somewhere in this region, the system was in thermal equilibrium. If the system is in thermal equilibrium, then most of the initial data gets erased. Right? You don't really need to know what it was before. Right? You only need a few details. What was the temperature? Right? What are the other conserved charges and so on. And then we can start evolving from here. So because of thermal equilibrium, because the system was in thermal equilibrium at some intermediate times, and we will see at what intermediate times we could apply thermal equilibrium criteria. But because of this feature, we can actually make predictions of what happened afterwards without knowing what happened before. Okay, so and we'll see how to make use of this.
So because of this thermal equilibrium, you also cannot predict anything about the past.
Well, not the average properties, right? But we will see that we can predict something about the past, right? Which are in terms of fluctuations. But average properties will be washed out. Other questions? Yes.
How can we say that in that region there is some thermal equilibrium happened or something like that?
How can we say? Well, we'll have to check if the number of collisions per Hubble time was sufficiently large. Right? If that criteria is satisfied, then we can conclude that there are thermal equilibrium in that region. Any other question? So from this, it should be clear that the main tool that you have to use in this analysis is statistical mechanics. Okay, in fact, mostly thermodynamics. Okay, not so much the details of statistical mechanics, mostly thermodynamics, but that's what you have to use. So what I will do is in the rest of the lecture today and maybe part of the lecture tomorrow, I have to give some review of some of the results of statistical mechanics that we're going to use. So for now, we'll forget about cosmology and just study equilibrium statistical mechanics. When you put it in cosmology, then of course you have to be always careful to check if the condition for applying equilibrium statistical mechanics holds. Okay? But for now, let's forget about cosmology and just see what happens if you have equilibrium statistical mechanics. So the main starting point in statistical mechanics is microcanonical ensemble. So you consider a gas with n particles, in a volume V, with total energy between E and E plus delta E. And we count the number of quantum states of this system. And we denote this by omega. Write the arguments in correct order, or omega E and V delta E. So omega is what I call the density of states. Okay, omega E and V is the total number of omega E and V delta E is the total number of states of the system between E and E plus delta E. Okay, it's typically a huge number because we are going to talk about systems with large number of particles in large volume. Right? Because you are going to take the thermodynamic limit at the end. In this system, we define entropy as E and V as log omega E and V. And this is what we call an extensive variable. Which basically means that it scales with volume. If you double the volume and double the number of particles and double the energy, okay, basically system, if you double the size of the system, then the entropy doubles. So this is stated by saying that S of lambda E, lambda N, lambda V is equal to lambda times S E N V. Or equivalently, we can say that S E N V can be written as V times some function of E over N and E over V and N over V. This is familiar to everybody? Right? We define entropy this way, and then we use the fact that the entropy is extensive. Okay, so it scales like this, okay, which implies this. So this quantity we'll call rho. That's the energy density. Okay, this is what we have been calling rho all through. This one is the number density of particles, so I call this N. Okay, so rho is energy density, N is number density of particles. These are intrinsic to the system. These don't scale with volume, okay, because of this ratio. So because of this, A satisfies this Euler equation dE del S del E plus N del S del N plus V del S del V equal to S. This is clear? Okay, this basically follows from this equation, right? This is true for all lambda, right? So you just change lambda to lambda plus epsilon and compare the two sides, and this is what you'll get. Okay, now some definitions. We define beta, okay, which is also 1 over kBT as del S del E. And I'll use units where kb is 1, okay, which means that when I talk about T, it will be really kBT that I'm talking about. Okay, kb I absorb in the definition of T. Okay. So just that's equivalent to each other, you just set this equal to 1. Mu is the chemical potential, which is defined as minus T del S del N, and the pressure is T del S del N. This is familiar? This P, is it the same as the P that we introduced earlier? The P that came in the expression for Tij. Remember, I introduced P by saying that Tij is equal to P times Gij. Right? In flat space, it will take Tij equal to P times delta Ij. Is it the same as this? Pardon?
Is P same everywhere in the system?
Yeah, it's system a uniform system, right?
But that P is different. It is a function of position.
Well, it could be if the system is not uniform. But if the system is uniform, it's same everywhere, right? See, I defined that P by saying that Pij is equal to Tij is equal to P times Gij, right? Let's work in flat space so that you can compare the two systems, right? So that P was defined as saying Tij is equal to P times delta Ij. Question is that P the same as this one?
Yes, sir. Depends on the coordinates.
Depends on the coordinate. Well, I'm using flat space coordinate. Flat space.
No,
Just Cartesian coordinates. Yes.
if you are using co-moving coordinates, then it's
Oh,
different. of
no
course.
cosmology, just flat space. Static Minkowski space.
Here I think the pressure is on the wall, right? This pressure of the microcanonical system, or there basically even we consider even in a slice within the system, and there we are considering pressure.
Cool. Why did you call it pressure?
Why?
Why did you call it pressure then?
No, we considered one surface area and
And there is
then counted how much change of rate of change of flux.
Momentum, yes, transfer of momentum.
Yeah,
Yeah.
And from that we showed that the P which we are taking is basically same with the pressure.
Yeah, that is same as the pressure, where pressure is defined as a force per unit area on the wall. If we take that system in a wall, then this is the force per unit area on the wall, right? That's what you prove. What about this P? Is it the force per unit area on the wall? This you should have learned in statistical mechanics, right? Not in GR course. You define P by this, right? But is it the force per unit area of the wall? Well, it is a force per unit area, but you have to prove this, right? And roughly the way one proves this, right, is you take, well, it's not a complete proof, but it goes a long way. You take a system, assume that there are two subsystems, A and B, okay, and then there's a moving wall in between. Okay, the wall can move. If you take these two systems, okay, they don't have to have the same temperature, you don't assume thermal equilibrium, but just assume that the wall can move. Okay. What will be the position of the wall, okay, in the final configuration? Right? It will try to maximize the entropy. Right? And just from that you can argue that this means that the pressure as defined on the two sides should be the same. Okay, so this is a mechanical, this definition agrees with the idea that when you have two systems, okay, separated by moving wall, okay, their pressure should be the same. Okay, that tells you that at least this goes some way towards the understanding that this P is the force that you are acting on the wall, right? Because when the wall is allowed to move, then what should be equal, right? in order for the world to be static, right? The forces that you exert from the two sides should be equal. And by maximizing the entropy, you find that the pressure should be equal. So that's how you establish that this is the pressure. Anyway, so we'll not say anything more. We'll pretend that this P is the same as that. Okay, so if you have a statistical system like this, we calculate P from this formula and substitute in the Friedman equation or in the conservation equation.
Please explain why the pressure of matter is zero. So, because the matter can also put some force on.
Yes, it can. We are talking about zero temperature, right? I mean, you remember that the matter that we have today, right, is cold matter. Its temperature is almost zero, right? That's why its pressure is zero. Right? The zero temperature matter don't exert pressure. Right? Even if you remember ideal non-relativistic gas, right? We'll see it later in relativistic case. Right? But take non-relativistic gas. Right? PV equal to nRT. Right? If T is zero, then the pressure is zero. Right? And the matter that we have today, right, is as good as it's having zero temperature. Right? But of course, when you heat it up, right, at sufficiently high temperature, it will also exert pressure. Okay, so these variables, T, mu, P, N, S, rho, right? These variables that we have introduced in this side. P is here. Beta I am not introducing separately because beta is just 1 over T. These variables are not extensive. These are intrinsic variables. When you scale up the system, these don't change. And these are the variables which are going to enter our cosmological equations. Okay, because cosmological equations will be using local equations, right? You don't care about the volume of the universe, right? That's irrelevant. Okay. So these will play a central role in the equation that we will write. But only two of these are actually independent variables of the system. Okay, so let me try to explain that. Only two are independent. So we need 4 equations, right? If you are claiming that there are only 2 independent variables, we need 4 equations that will direct them. Okay, so where are those 4 equations? So first, let's look at this equation. Oh, S I didn't introduce, no? Okay, what is small s? Small s is just entropy per unit volume. Small s is S over V. Okay, so let me write down all the definitions in square brackets so they don't get lost. So here, so these are 3 variables. This is the 4th variable, and then these are 2 more. Okay, those are the 6 variables you have introduced. So N, S, rho. This is number density, entropy density, energy density. P, mu, P are related to the derivatives of the entropy with respect to energy, number, and volume. So the first equation comes from here. This equation tells us that S is function of rho and N. function is returning from statistical mechanics. Okay, this in fact plays the role of the equation of state. Okay, knowing this function, you can work out the relation between P and rho that we have been using earlier. So this is equation number 1. Equation number 2 is this one. Okay, let's look at this equation. Okay, and try to divide everything by V, right? So that it scales not as lambda but lambda to the 0. So this equation tells us that E over V times del S del E. What is del S del E? It's 1 over T. It's beta. Right? Times 1 over T plus n del S del N. N del S del N. So N over V, that is small n, and del S del N is minus mu over T plus you divide by V, so you only have del S del V. Del S del V is P over T. P over T is equal to S.
But is it not that the second equation, whatever you have written S as a function of S, F and function F, and the second one, both are basically turns out to be the property of the extensive quantity. Means since S is an extensive quantity, so
Yes.
that basically gives both the equation, right?
Yes. So starting from here, you could have gotten both the equations. We'll see.
So whether those are really independent equations?
Oh, these equations are independent, clearly. We'll see. Okay, depends on what you mean by independent equations, right? So far, okay, let me write this equation. So this tells us that S is rho over T minus, let me write it as rho minus n mu plus P over T. Right? So this equation certainly is independent of this equation. Because so far you have not written any other equation between relating this mu with anything else, right?
Yeah.
Right? So from that sense it's independent.
But somehow both the equations came from the same property, that S is extensive quantity.
Yes, that's true. So we'll recover this equation again in another way. We'll see.
So when we compute this, the first equation from microcanonical ensemble,
Yes.
mu and p will not occur there. That's why.
Yes, exactly.
Yeah.
So S will get a function of rho and n. Right? The mu appears in this equation. So clearly this equation cannot be dependent on this one, right? Because that doesn't even know about mu. So this is the second equation. The other equations will come from here. Okay, so let's try to do that.
But sir, here mu and you have told that only two are independent, so mu and p can depend on rho and n.
So
this
we have
equation
to try to prove that two are independent. I just stated it, right? I have not proven it. So what I'm trying to do is to write down 4 independent equations, right, among these 6 variables, so that it's clear that 2 are independent. Right? So far I have got 2 independent equations. Right? Now I'll write down 2 more. Right? So that tells you how to eliminate everything in favor of the 2. Okay. So the other equations come from the following. Let's look at the variation of S. Arbitrary variation of the thermodynamic variables. We vary S. So delta S is given by del S del V times delta V plus del S del V times delta E plus del S del N times delta because S is a function of these variables E, N, and P. But I don't want these capital S's. Okay, let me first do one thing. Let me write this. So del S del V by definition is P over T. So this is P over T delta V plus del S del E is 1 over T delta E, and del S del N is minus mu over T, so minus mu over T delta N, minus mu over T delta N. But the idea now is that we will try to write everything in terms of these variables. Try to eliminate the extensive variables. So I'll write this. So S is what? S is V times S. Right? Small s is capital S over V. These are S, no? So you can write this as V delta S plus S delta V is equal to P over T delta V plus 1 over T. Delta E I can write as rho delta V plus V delta rho, right? Because E is V times rho. And minus mu over T delta N I can write as N delta V plus V delta N. Okay? So this tells us that delta S, I take everything from the other side, is given by, first there is a term delta V over V. Let's count all its coefficients. Delta V over V. So you get minus S, where it goes to the other side, plus P over T, plus rho over T, minus mu N over T. Plus, from here, delta rho coefficient, V we are dividing by, so 1 over T delta rho minus mu over T delta N. Is this clear? What I did? I just took S delta V on the other side, right, and just divided by V to calculate delta S from here. Okay, and collected the coefficients of delta V over V, then delta rho and delta N. First term is identically 0 because of this equation. Okay, and essentially that's what Mr. was trying to say, that it shouldn't be independent, right? We do have this automatically 0 as a consequence of that, right? So even if we didn't use the Euler equation, okay, just by comparing the coefficients, we could have said that this is 0. Okay, thinking of V, rho and N as independent variable, right? Instead of V, E and N as independent variable. So this tells us, so this gives you the delta S is 1 over T delta rho plus minus mu over T delta N. So we get two more equations. 1 over T is del S del rho, but S is given by this function f rho n. del S del rho plus del F del rho. And minus mu over T. So this is the third equation. And minus mu over T is del S del N, which is del F del N. Is this clear?
Could you repeat the last step?
Pardon?
Could you repeat the last part?
This one? Oh, so I have this equation, delta S is 1 over T delta rho minus mu over T delta N. Okay. Now I can think of S as an independent function of rho and N, right? Because of this equation over here. Right? S is an independent function of rho and N. So I just compared the coefficient of delta rho. So ds, so you compare this with delta S equal to del S del rho delta rho plus del S del N delta N. Right? By comparing, I get del S del rho is 1 over T. Right? That's this equation. And del S del N is minus mu over T. That's that equation. So these four equations, okay, which we'll have to use extensively during the analysis, tells us that we can take any two of these six as independent variables. Is this clear? Now this is somewhat in contradiction to what I had told you earlier, right? I had said that for a given component, right, we have these two variables P and rho, right? And equation of state gives one in terms of the other, right? So if we believe that, then we would have concluded there is only one variable per component. Right? Here you are saying there are two variables per component. Right? So what has gone wrong? Where did our counting go wrong? Okay, confusion, yes. So you agree that I had these six variables, okay, and I derived four equations, right? So that shows that I can express that once this function is known, given, right, I can express everything in terms of two variables, any two, right? But earlier when we were doing cosmology, right, we had said that for every component, right, we have only one variable. Because you had rho and P and then eliminated by the equation of state rho in terms of P, right? So somehow you had missed a counting, right? So what did you do wrong there? How could you get away with introducing only one variable per component instead of two variables per component?
The independent conservation.
Independent conservation?
That took
Well,
out
yeah,
time.
independent, but that was of course cosmological equation, right? We are not talking about just statistical mechanics.
So by the equation of state, we can use equation of state.
Yeah, equation of state is analog of this, which we have already used, right? Thereby using equation of state, we got rid of one variable, right? And we said there is only one variable left. Here, after using equation of state, we are still left with two variables. But the point is, we didn't do really anything wrong there. Okay? What happened, okay, was two different things for two different components. Okay, let's look at the matter. Okay? So for the matter, okay, we used what entered the equation of P and rho. Okay? But the matter component has one extra variable. Okay? and that is the number of particles per unit volume. That just didn't enter our equation, right? But it certainly is there as part of the knowledge, right? We didn't need to use it. If you have a matter, suppose you have matter, we give the energy density. Rho gives you the energy per unit volume, right? Which basically comes mostly from rest mass energy. Okay? But we also have an independent variable, that is a number density per unit volume. If the energy was coming from protons, it is one kind of number. If it was coming all from electrons, right, then there will be another kind of number. Okay? So that information certainly is part of the description of thermodynamics of the system. Okay? It's just that information didn't enter the cosmological equations, right? The Friedmann equation didn't need it, okay? And the equation of state that we used didn't need it.
Yeah, it is rho by m for matter.
It's rho by
M.
yes, it's rho by m for matter, but there may have been many different kinds of m, right? We
Here
don't know.
we have only done the computation in thermodynamics, right? We have to do really a statistical mechanics counting where basically this n and rho are related, how they are related, right? Which kind of particles are there and
But we are not
corresponding to which
we are
energy.
not claiming that they are related. They need not be. That knowledge is not needed. Right? We have to think of n and rho as independent variables of statistical mechanics. Right? See, n would have entered. Okay? N would have entered if you had been working with finite temperature, because we had said P equal to 0. Right? But P is not 0 for matter, right? P is NKT. Right? That n would have entered if we are doing thermodynamics, right? So the equation of state, I said that I can use equation of state to relate P and rho. Okay, that is not quite correct. Okay? I had said P equal to 0. Okay? It was fortunate that because the temperature was almost 0, right? I didn't need the knowledge of it. Right? That's why we didn't see it.
So for radiation, what?
Yes, for radiation, what happened? There is a finite temperature.
The entropy density will come in.
Entropy density will come in, yes. So how will it come in? See, entropy density didn't enter Friedmann equation directly, right? So why didn't we need knowledge of two quantities for radiation? Right? Because this zero temperature doesn't work for radiation, right?
For radiation, we have simple equations for entropies and all related to T, right?
Why?
So,
Why?
hmm?
Why? I said there should be two independent variables, right? For matter, you know there are two independent variables, right? Even though one variable was not entering the Friedmann equation, right? That's why we got away.
So for radiation, you can take mu equal to 0 and P and rho are related, and then
Yeah.
S
So the point is,
related to
for
T.
mu,
so
for radiation, there is an additional equation. That's mu equal to 0.
mu equal to 0.
Right? Why is mu equal to 0 for radiation?
Number is not conserved.
Number is not conserved, right? So that is the additional data for radiation that allowed us to get away with one variable, right? So the reasons are different. Why matter, actually there is an additional variable, okay? It's as though we didn't need it, that didn't enter. Okay? For radiation, we didn't need it because mu is 0. Okay? So there is actually one variable, not two, for radiation. Is this point clear? Okay. So let me just end by making this a little more clear. What happens if n is not conserved? So if n is not conserved, then in statistical average, we sum over n. Right? Which means that if you are trying to calculate the average of some quantity O, thermal average, right, we calculate it by saying that we sum over n omega E n V times O divided by sum over n omega E n. Right? Because you don't keep n fixed. Right? When you talk about, when you count the number of states, we count for all possible numbers. Okay, and do the average. This I can also write as sum over n e to the s E n v and so divided by sum over n e to the s E n. But of course, in actual practice, when you do thermodynamics, okay, in thermodynamic limit, this sum over n gets contribution only from a very narrow range, about some mean value. Okay, that's thermodynamic limit. How do you determine what that mean value is? Where the maximum contribution is coming from in the sum over n? What is the principle that we'll be using?
Extremization of the entropy.
Extremization of this. Whenever this is maximum, that's where the maximum contribution is going to come from, right? Because this is a highly peaked function, right? A sharp peak, right? So you basically have to look at where this is extremized. Right? So I can write this roughly as O for some n, let's say n bar, where this n bar is determined by saying that del S E n V del n equal to 0 at n bar. Right? So the place where it's peaked, okay, it's so effectively you can think of n bar as fixed, okay, except that it's not up to you to fix it. Okay? It gets fixed by extremizing the entropy. And this is precisely the mu equal to 0 condition. Right? If it was if n was conserved, you would have defined this as the minus mu over p. So if n is not conserved, you can pretend as if n is conserved, you can introduce your mu, but at the end you have to set mu equal to 0. Right? That's the meaning of having non-conserved charge. So this implies that you have mu equal to 0. Okay. So the point is that a system with conserved charge and not conserved charge, okay, can be treated more or less equally, okay, provided at the end you remember to set mu equal to 0. Okay. You don't think of mu as an independent variable, you set mu equal to 0 at the end. Is this point clear? Now, we'll see that when you have to deal with cosmology, right, you have a much more complicated system. It's not that you have individual components where a charge is either, number density is either conserved or not conserved. Okay. Typically what will happen is that you have a mixture of many components, okay, and some combination of those numbers may be conserved. Okay. Just as an example, okay, at sufficiently high temperature, you will have electrons and positrons in the gas, right? The number of electrons, is it conserved? Is it conserved? No. Because it can have pair production, right? Number of positrons is also not conserved. But the combination of them is conserved, right? You cannot create electrons out of nothing, right? You can create electrons provided you also create positrons. Right? So number of electrons minus number of positrons is conserved. And so, we shouldn't have two independent chemical potentials, because that will imply independent conservation loss for electrons and positrons. You should have only one chemical potential, but which one? For the electron or for the positron?
Will
be same for both.
Yeah, so basically we will see, well, it need not be the same. We will see that there is a relation between the chemical potential for the electron and chemical potential for the positron. Right? When you say it will be the same for both, right? You are assuming that the total number of electrons plus the total charge is 0. Total charge carried by electrons and positrons is 0, right? That need not be the case. In fact, in our universe, it's not true that total charge carried by electrons and positrons is 0, right? There is excess electrons, right? So the chemical potential should not be, so there will be a relation between the chemical potentials of the electrons and positrons, right? And we will see next time how to figure out that relation. Okay. So at the end, the upshot is that this is what the counting will do more carefully next time. Okay. So the upshot will be that after you put in all these constraints, okay, you will find that you always have the correct number in thermal equilibrium. Okay, you will always have the correct number of equations, okay, as the number of variables. Okay. Either some variables are absent, okay, in which case you have some equations missing. Okay. If the variables are there, then there is also corresponding equation. Okay, so we will do this counting more carefully next time. And also next time we will try to redo this analysis using grand canonical ensemble, because the actual calculations are all done really in the grand canonical ensemble. Right? The calculating this omega is very difficult, typically. Okay, we can calculate thermodynamic quantities in statistical mechanics by using grand canonical ensemble. Right? So we will repeat this analysis in the grand canonical ensemble, and then we will see how to set up the cosmological equations. Are there questions? Then we'll continue tomorrow.